Welcome to lecture number 8. In this lecture, we're going to talk about MATLAB and SIMULINK, how to do various things within this very important platform. So that's the topic for this lecture. In terms of the content, we're going to talk about some of these topics: polynomials, partial fractions, LTI objects, such as transfer function and ZPK, the C2D, Bode plots, FFT and the FRD, and PINV. So those are some important things we're going to be talking about. So let's get in and look at MATLAB. MATLAB is an important programming environment for engineers and scientists. So the version I'm using is MATLAB R2014A. There are more recent versions than this, but this is the one that I have access to at this point. So I have the control system toolbox, I have the symbolic math toolbox, so I'll be talking about some of the functions associated with those. Now, as I mentioned, this is an essential tool for especially controls engineers and many different kinds of scientists. Control engineers also use software such as MatrixX. That is a very common software. Some engineers use Maple or Mathematica to do symbolic calculations, or MUPAD. And for simulations, some engineers use LabVIEW. Okay, so MATLAB also has its companion toolbox called SIMULINK that allows the simulation of block diagrams. So we'll be talking about that as well. So these are essential tools for controls engineers. Now, in terms of MATLAB topics, as I mentioned, this is MATLAB 2014A. So this has certain features that previous versions might not have. So I believe the computers in the College of Engineering, anything that has a recent operating system like Windows 8 is probably going to have, I think, MATLAB R2014A, maybe 2014B. So if it works under 2014A, it probably will work under 2014B, but not necessarily vice versa. So, and what works under 2014A might not work in earlier versions, or it might. It's difficult to say how the changes go. So anyway, okay, so I'm going to start off with a new script, so just so that we can have a running example of what we're talking about. So the first thing I want to talk about in MATLAB are polynomials. So for polynomials, we have we can define a polynomial such as a numerator as 1, 1, 2. This would give a polynomial. Let's say 2 times that. And a denominator here I'm going to define this way. So here, this basically is a polynomial where this is generally thought of as the zeroth order, the zeroth coefficient. This is the first coefficient, the second coefficient. So polynomials are usually described in terms of descending order of their coefficients, the powers. I can also define a polynomial this way. So notice that in defining a polynomial this way, I am basically specifying it according to its roots. So this polynomial then is going to have roots at -1, -2, and -3. Okay, so I can go ahead and run this, and we can see the result over here eventually. Oh, it wants me to save it. Call it example 1. And it's running example 1. Okay, so this is the polynomial I get, and that polynomial will have these roots. Okay, so we've defined polynomials. Okay, so we can also define polynomials this way. Let's say numerator is equal to convolve 1 minus 1, 1, 3. Okay, so convolve, basically, so this multiplies a polynomial s plus 3 times s minus 1. And so I can form polynomials that way as well. So these are a number of different ways of defining polynomials. Okay, so having defined these polynomials then, I can also include so I can convolve this, for example. Oh, wait a second. Let me just go ahead and do it this way. So if I wanted to include a pair of complex poles, I could do 1 plus 2 times, or 3 times j. And if I include a complex pole, I need to include its conjugate as well. Okay, so we run that. Let's do roots of den. And so I can see that I have minus 1 plus j3 minus j3 minus 3 minus 2 and minus 1. Notice that I have the format of the display set to be long. I'm going to set it to short. Up arrow, up arrow. I'm going to do the roots again, and so it's a little simpler this way, and so I can see more clearly what the roots are. So there are advantages to having a long. So I can do format long, in which case I can see more digits, or I can do format short and see fewer digits. In this case, it rounds, and when it rounds, it comes closer to what we're expecting. So notice that when you have complex eigenvalues, or roots rather, it will give you the real and imaginary part. Okay, and if any of them have an imaginary part, they then all of the roots will be considered to have an imaginary part, where the imaginary part may be 0. Notice also that it uses the I notation as opposed to j. So even though when I defined it, I used j to define the complex, it actually prefers the use of I. So both I and j are predefined in MATLAB to be the complex number square root of minus 1. Okay. If I have a polynomial, for example, this polynomial here, and I want to evaluate, let's say s is equal to j times 2, I want to evaluate that polynomial at this value of s. I can do polyval, numerator, that value of s. I can do it at a single value of s, or I can do it at a vector of s, in which case it will return a vector when I do that. So when I do it this way, it returns a value. So here's the value that's returned when I use that s. So notice in this case, I put in a complex value for s, plug it into the numerator, and I get a complex value out. Okay, so that's a typical for evaluating a polynomial, even if it has real coefficients with a complex quantity. Okay, so I'm going to comment that out. So polyval is helpful in evaluating a polynomial at some value of s, of course. Or it could be a polynomial in z, and you evaluate it at z. Okay, so any kind of, so the polynomial basically is a row vector. It's understood that is a polynomial, even though it is actually a mathematical description. The next thing I want to talk about is partial fractions. Okay, so let's say we have a transfer function with this numerator, this denominator. I'm going to go ahead and comment that out. now. So I have this numerator and denominator, and I want to do a partial fractions for that rational function. I can do RP equal residue of numerator and denominator. So basically what this does is it does partial fractions. Okay, so when you execute this you will get R values and P values. Okay, so the R values are the coefficients, the numerator of the partial fraction term. So this is the coefficient that goes over this pole. This coefficient goes over this pole. And notice this coefficient here is actually 0. And it goes over this pole. And it's like, well, why did we get a 0? Well, if you went back, if you notice, I have a pole at -3 and a 0 at -3. And so we actually got a cancellation occurring. And so that's why I ended up getting a 0 there for the residue value. Okay, so the R values are the coefficients, the P values are the pole values. Okay, so I can do partial fractions. Now notice the partial fractions, when we do it this way, is really only associated with a like a Laplace transform type of partial fraction expansion. So notice when you use the Z transform or the Q transform, we actually have different needs as far as partial fractions. So that is, when we do partial fraction, when we do an expansion, in order, for example, to do like an inverse Laplace transform or something like that, we generally want the partial fractions to be given in terms that are similar to terms that we would find in a Laplace transform table. Okay, and so in the case of Laplace transform, that works, but Q and Z transform, not so much. Okay, so this does partial fractions. Okay, here I'm going to do another function. Dan is equal to poly -4 times. So notice that now I have basically four poles, and they're all at -4. Okay, so look what happens when we do the residue. Okay, so in other words, we have repeated roots. Okay, so notice that the roots are essentially all at -4. Notice that these have tiny imaginary values, and the reason is that when you have repeated roots and it's trying to, it doesn't know ahead of time that they're exactly repeated, and so it does its best guess, and its best guess is sometimes off a little bit. Okay, so in this case it's off in a complex direction. In this case it's off in the real direction, and this one similarly. Okay, so they're all kind of clustered around -4, but they're not. Any of them are not exactly at -4. And look at these residue values. We have some large values here associated with this. 10 to the 9. Wow. Okay, so anyway, this is the partial fractions that we get when we have repeated poles. So incidentally, if you look at the original denominator, it has, it's got large coefficients here, but notice the coefficients are nothing like 10 to the 9. Wow, that's remarkable that we get that. And part of the reason that we get such large values is because we have this clustering of roots. And so whenever you have repeated roots, numerically it's very difficult to distinguish one root from another, and so numerically there are lots of problems with in a situation where you have repeated roots. Okay, well, generally, when we have a numerator and denominator, it's going to be the numerator and denominator of a transfer function. And so that brings us to the topic of the LTI objects. And so I can define, for example, system1 to be equal to the transfer function with numerator and denominator given by num and den. I just call it num and den just because I know num stands for numerator for me, and den stands for denominator for me, and so I just always use those. But you can call it whatever you want. You can call it Fred or Quack or whatever. But so when we run this, this is the transfer function, and by default, so notice that it recognizes it's a continuous time transfer function. By default, it puts the polynomials in expanded form. Okay, so you can see the expanded form. So that is the default. Now we can put this, we can display this in the ZPK form, zero pole gain. Okay, and so when we run that, so notice that it was smart enough to recognize that it had repeated roots at 4. So in this particular form, it actually recognized that. So this is a little bit more intelligent than the roots calculation. And part of the reason is that it actually does some approximating when it does this. When the values are very close to being integers, like these, then it just assumes that it's an integer, and so it kind of rounds and truncates and stuff. So notice here it says zero pole gain model. So notice here's the zeros, here are the poles, and there's the gain. So that's the ZPK, zero pole gain. K is gain. I would say ZPG, but anyway. So that's the zero pole gain, and you can enter a transfer function in terms of its zero poles and gain, but generally speaking, it's easier to put it in terms of its polynomials. To enter the polynomials and then define it. So here I have a transfer function. So ZPK. So suppose now I have a system, an LTI object, and let's say I've defined it somehow, and let me define it another system. Okay, so there's my second system. I'm going to define now sys3 as sys1 plus sys2. So sys1 is a transfer function, and I can do transfer function algebra. So that is, this is a fraction, this is a fraction, it's going to add the two fractions. So let's see what happens when we do that. Boom. So notice again, by default, it puts everything into expanded form. So I could do ZPK of all that. And you can see it still recognizes that we had those 4 repeated roots, and then notice that the numerator, it didn't factor so cleanly, and that's probably because when we add the two polynomials, you don't get a nice factorization. So it factors it, but the factorization isn't quite as nice as, for example, this, where we had integers. So and that's a consequence of adding two fractions. So the denominators are nice, and notice the extra transfer function I added had these poles, had one at s plus 1 and s squared plus 1. So it just so happened. Complex poles. Okay, so I can also do, I can do notice there I did addition. This will also do multiplication. Watch what happens. So notice when we do multiplication, then everything actually is simpler, the way it's defined, because my original function had these three terms, and so it was able to keep them, and then my new function had these terms, and it was able to keep them. So when we multiply it, it actually is able to keep those forms. Okay. So at least add and multiply. Division doesn't quite make sense for systems. Okay. Addition makes sense, multiplication makes sense, division not so much. So I'm curious what happens when we do that. Well, gave us a system. Boom. So it must have turned it upside down and gone with it. So yeah, it works. All right, so we can actually do division too. All right. Okay, so that's ZPK. So now we have this system, sys3, and I now want to extract its numerator and denominator. So maybe there's something I want to do with them. Then I can do this. I can do num3 den3 equals tf data sys3, and here the v means it wants them returned in vector form as opposed to cell form. So MATLAB has a number of different data structures that it uses in defining things, and so the cell form is one way, and I don't particularly care for it, but so I prefer it in a vector form. So this would give it that way, and so we can extract the data. So there are the two polynomials. Now it's very common for you to get leading zeros when you do this. So you might, if you're going to extract these polynomials, you may need to be prepared to remove that extra zero out front, that leading zero, because it'll basically make these two polynomials the same length. Okay, so you can expect that. Also, notice that the original polynomials were all integers. These should have all come out to be integers, but again, there's some round off and stuff like that, and so these are actually integers, but they have very, very tiny fractional portions. So, all right, so that's TF data. Now, suppose I have a system and I want to incorporate a time delay into the system. I can do, for example, sys2 set sys2. Let's do sys1. IO delay. So let's say it has a time delay of 0.1 seconds. So it'll do that. And when you run this, notice it runs it. But so even though I didn't put a semicolon at the end there, we don't necessarily see that time delay. It doesn't display sys1. So if I want to display one, I have to actually manually do that. And so notice that it recognizes the time delay as e to the minus 0.1s. So there's the time delay for our system. Okay, so this will do time delays as well using the IO delay property. So these are basic manipulation routines for LTI objects. Now there are a number of important things that we can do with these. So the first thing that's important for us is that we can do the H transform for systems. MATLAB understands the H transform and will correctly do that, apply that to a system. So we can do that using the command C2D. So here sys1 is in continuous time. I can say sys1D is I use the D just to indicate it's discrete. C2D, continuous to discrete, sys1, and then we have to supply a sampling period. So let's suppose our sampling period is 0.055 seconds. Okay. So what happens when we run that? So we get the result, and notice that it takes into account the time delay of the system, and it returns it all in the z domain. Okay, so MATLAB in previous versions understood the Q transform. It doesn't quite do it right anymore. So, but you can do the same kind of thing that we talked about. And so here it's in the z domain, and notice that because of the time delay, we get these. This time delay translates into these extra z inverse negative powers out front, and so, which is fine. This is actually true, but generally speaking, we want these lumped in with the transfer function, and so we in order to lump those in with the transfer function, we need to use I can do this now. Sys1d is equal to delay to z sys1d. And so now when we display that, so notice that it had those negative powers of z, so basically it put multiplied the denominator through by z squared. Okay, so that's what we have. So it tells us it's a sampling time is 0.05 seconds, discrete time transfer function. So basically, it just lumped those into the overall transfer function. So now, how do we display this transfer function in, let's see, I'm going to comment. I'm going to go ahead and comment this guy out so it doesn't keep displaying all the time. How do we display this in the Q domain? So we can actually, well, we can't actually do the Q domain directly, but remember, Q is equal to z to the power minus 1. So we can do it this way. Set sys1d variable z up angle minus 1. Okay, and so when we do that, sys1d, let's see what happens. So here's the original z version. When I do that command, when I set it, I get this. So notice it's now in powers of z to the power minus 1. Okay, powers of z inverse. Okay, and so this is the form that we would use to have it in the z domain. Okay, in the Q domain as opposed to the z domain. So this would be z cubed, z to the power 4. I'm sorry, q cubed, q to the power 4, q to the power 5, q to the power 6, and so forth. Okay, so this is our. So notice that in this case, q to the power 6, that's of order higher than the denominator, which is q to the 4. Okay, so we have that. So we can actually have it represented in the Q domain, but we have to keep in mind that Q is equal to z to the power minus 1. So I can do that. So C2D, it understands that, and again, an important part of C2D is that it recognizes time delays. So if my system happens to have a time delay in it, the C2D command can do what's needed to do that. In other words, the modified H transform, which is needed to do that, it understands and it uses it. So that's cool. Okay, now we have a system, and we can discretize it. So now what? Okay. What do we do with the system? Well, suppose we want to then take the step response of that system. We can do step of sys1 and say sys1d. So notice that sys1d is the discrete time version of sys1. When you use this, so I can include as many systems in here as I want, and it will basically put the step responses of all those systems on the same graph. So we run this, and notice it's busy down here. It's got to think about it. The first time you run a new function like this, it takes a while. Okay, so here's the result that we get, and you can see that it has a time delay. Notice that it doesn't respond until 0.1 seconds, and then it starts going. And notice I have two responses. The blue response is the continuous time response, that's sys1, and the green response is the discrete time version, the zero order hold version, or well, it's a discrete time version, and so in order to plot it together with the continuous time version, it creates a continuous time version, and it uses a zero order hold to do the plot, so we get a stair step. Notice the two match exactly at the sampling times. So the sys1d is an exact approximation. I mean, it's an exact discrete time representation, and it's exact at the sampling times. Notice that in between sampling times, the two responses are different, okay? But at the sampling times, they're identical. And we see it's actually shifted a little bit. It's held constant in between samples, so the zero order hold property. So we can do step response. We can do impulse response. So that's the impulse response. Boom. So notice that the impulse response and the step response aren't necessarily equal at the sampling times. Okay, they're not necessarily equal at the sampling times, and that's because of the fact that that the zero order hold approximation really is only as a piecewise constant approximation is really only good when you have a constant input, not like an impulse. So the impulse is something that is a little different. I can also do something called LSIM, and actually I don't know if LSIM will do this. Help LSIM. So it looks like you can. Looks like you can do more than one system. Yeah. All right. So let's define an input. Let's define a vector t. So our sampling time is 0.05. So let's do t is equal to t times 0 to 50. And let u equal cosine 3 times t. LSIM ut. So this will simulate these systems with those inputs at those times. So it's busy doing it. And so here's the response that we get. And I don't understand. I'm guessing the gray is the input. And then these two, the blue and the green, are the outputs. Let's see. Yeah, I'm not sure why it I'm not sure why it has that gray in there. There's probably some parameter that you can set. That's a new thing that I hadn't seen that before. So MATLAB surprises us sometimes. So we can zoom in by using this this tool, and so you can see how it goes. So again, the green and the blue don't necessarily match up because the zero order hold really only works with constant types inputs. And so if the two are not the same, then you will get a different response. So you can see it is in fact different. Okay, so LSIM, impulse, step, those are the standards that we can. So LSIM, you can let the input be any kind of function. Okay, You can let it be any kind of function. So, in addition to simulation type plots, we can also do Bode plots. Again, it has to think about it, because the Bode plot is a new thing it hasn't done before, and so it has to think about it. So let's, okay, so there we go. So the Bode plot, the green and the blue. So the blue is the Bode plot of the continuous time system. The green is the Bode plot of the discrete time system. And you can see for frequencies below a certain point, they're basically identical. But up after a certain point, the magnitude of the discrete time veers off. But notice when it does veer off, it does so at fairly low magnitudes. Minus 50 dB, below that, that's actually pretty low. So it's down in the noise, or down in very small signal levels. Also, notice this black line here. This black line corresponds with the Nyquist frequency for our system, our discrete time system, which has a sampling time of 0.05 seconds. And so this line is the Nyquist frequency. So the Bode plot for a discrete time system is only valid out to the Nyquist frequency. Now, when I have a Bode plot like this, if I do a right click, I have some options, and it's not letting me do. Huh. Anyway, it's not doing what it usually does. Kind of weird. Anyway, a right click will allow you to check certain parameters, such as peak response and things like that. So that right click can be helpful here. So Bode plots. We can do Nyquist plots and other plots. Okay, so that's important. Let's change our input. Now I'm going to let n equal 2 to the 14 power, and I'm going to be n minus 1. I'm going to have a large amount, and I'm going to change u to be something like this. So the input now is a signal that is, so rand gives us a normally distributed random vector of length n rows, 1 column, and then sign basically, if the number is positive, it gives the number 1. If it's negative, it gives the value minus 1, and if it's 0, it gives the value 0. So this can take on one of 3 values: minus 1, 0, or 1. And so this is one way of creating a random binary sequence. This sequence will switch randomly between plus and minus 1, basically. Okay. So I'm going to take this signal now, and I'm going to comment this out. I'm going to simulate the system with it. So I can do this. Y is equal to sys lsim sys1d ut. So when I create an output for this command, it now will return the value and not give a plot. Okay, so it'll do this simulation, but instead of plotting it, it'll return it. And so notice here, since I'm using the sys1d, this vector u is assumed to be a continuous, a discrete time signal, and this output now is a discrete time signal. Okay, so we now have a discrete time signal for this, and so let's plot it. So I'm going to do, I can bring up a figure 1. I'm going to do subplot 2, 1, 1, and so subplot basically allows us to take our figure window and break it up into pieces. Okay, so what this says is I want 2 rows of plots, one column of plots. So that's 2, 1, and then this is the first plot. Okay, so the plots generally go across each row, and then down to the next row. So in this case, the first plot is the top plot. The second one will be the bottom plot. So now I'm going to do subplot 2 and 2. So when we run this, it brings up the plot. And it's like, wow, that's a lot of noise. Well, remember, it's a random sequence, so it is basically noise. So the U, notice it switches between -1 and 1, and it's switching a lot. We have a lot of values in there, okay? And so it's switching a lot. It's sometimes valuable to be able to set the axes so that we can actually see the signal a little clearer. So I'm going to set the axis. So 0 to -1.2, 1.1, 1.1. So n times t, it takes the so it starts at 0, goes up to n times t. So remember, we have, that's basically the last value here, and then so this is the x-axis. I can set my plot, the x-axis, to look at a specific portion. The y-axis, it's going to go from -1.1 to 1.1. Okay, so when we run this, did I spell it wrong? There. Okay, so I can actually see the top edge here, where I couldn't see it before. So now, if I zoom in on a portion of this, I can actually see the switchings, and so you can see sometimes it's high, sometimes low, and it switches at somewhat random times. So I can zoom in on what's going on with that signal. Okay, so and then this signal I can also zoom in if I want to see the values. So I'm basically applying something like a noise, but it's a very specific noise to our system. And you can see when you do that, the system just kind of vibrates and just kind of does whatever, and but it's organized because we're doing it on purpose, right? Okay, so that's this is the time response that we have. We can actually plot that. So this is the time response. I want to now talk about the FFT. So So I can define, for example, y equal and notice that because we chose the number of data points to be a power of 2, we actually get an efficient calculation. It turns out that for this many data points, MATLAB is definitely fast enough to be able to handle it, and you can hardly even tell the difference. If in other words, if it weren't an exact power of 2, then it would still be able to do it pretty efficiently. Okay, so now when you do the FFT, it takes 2 to the n values and it returns 2 to the n values. But the frequencies over which it operates are basically the frequencies equally spaced around the unit circle. So remember, in discrete time, the unit circle values correspond to the values of the stability boundary, but they also correspond to the values of frequency. Okay, so we have that, and so, but this goes all the way around the unit circle. It turns out that because of symmetry, the part on the upper half of the unit circle is the conjugate of the part of the lower part of the unit circle. So really, the only unique data is the upper part of the unit circle. So we only need half of the data values in order to accurately see what's going on with the FFT. So I'm going to go ahead and extract those values. So y equals y of 1 to n divided by 2. Similarly with u. So I have the FFTs of y and u. And so if you remember what the transfer function is, the transfer function is y over u. And so I'm going to define p to be y dot divide u. So remember, because these are data vectors, these are in the frequency domain, then I need to do a dot divide in order to do the element by element division. So this is an estimate of the transfer function of our system. So remember, the system was actually sys1d. And so this is an estimate of our transfer function. Okay, so this is in the frequency response. Now, if I want to actually plot this, I need to define a frequency vector. So pi divided by t. So that's the vector. That's the Nyquist frequency. So the frequency is all the frequencies in the Nyquist up to the Nyquist frequency. And I need n divided by 2 of them, since I'm only going to look at n divided by 2 values. So I go from 0 to n divided by 2. I'm going to make this a column, and then divided by n divided by 2. And actually, minus 1. I need to subtract 1 because otherwise I get 1 too many. And so I now have the estimate of the transfer function at the frequencies, and these are the frequencies they're associated with. So now I can do a Bode plot of this system, and I can do that by creating something called an FRD. I'm going to say P is equal to FRD of P comma W. So I'm going to take these values and I'm going to create a frequency response data LTI object. Having defined that, then I can now do Bode of sys1d and P. So these are both LTI objects, and I can now compare them. So I'm going to go ahead and do, before I do that, I'm going to do figure 2. So I have this on a separate figure. Okay, so here's the figure that I get. And so we have the Bode plot. Now, our data is such that we get a lot of data at what looks like high frequency. And so I can compare the two. And so the green is the frequency, the plot I got from the frequency response data. The blue is the Bode plot of sys1d. And you can see that they're basically the same. Notice that the frequency response data is noisy. And again, that's because the FFT is an approximate of the Fourier transform of that signal. And so as an approximate, it actually generates something like noise. And notice we can get some fairly large values of noise. But you can see it overall, it roughly fits the transfer function. And so we're going to find that this FRD object is going to be a useful way of being able to compare a transfer function that we get by system identification with the data that we get. And so this is going to be a helpful thing. So this is the Bode plot, and we've now introduced the FFT, how to use the FFT, and also the FRD. Okay, so that's important. Okay, the next thing I want to show you in MATLAB uses an important command we're going to be doing in terms of being able to obtain a model based on data. So in this particular MATLAB M file, I've cleared away the other one, and I have this new file. I have 25 data points. I form X and Y. X and Y come from that. And so Y is equal to 3x plus 2 plus something small, 0.01 times, again, this is a random number generator, normally distributed. That's what the n stands for. I have n values. So basically, Y here is related to X. It's linear. It's almost a linear relationship, except it has noise. So what I want to show you is how to do curve fitting using MATLAB. And so here's X and Y. So this would be, for example, from some measurements that have been obtained. We want to find. So let's suppose this is X and Y obtained from some experiments. So then we're going to have data. How do we extract Y, or rather, how do we extract a model from this data? So we form our regressor X, which is of this form, which you will learn about later. And then we use the pseudo-inverse of X times Y. That gives us our unknown parameters, which can be used to form a polynomial. So this is a column. This converts it to a row. So then this becomes the polynomial, and so now we can recreate the data from X using this polynomial, and we can compare the two. So that's what all this is about. So when we run this program, we get this plot. So the O's here are the original data, okay, and then the blue line or the green line here is the curve fit that we've just come up with. Okay, and as you can see, it fits pretty well because the noise is actually small. If we increase the size of the noise, okay, so instead of 0.01, it's 0.1, you can see that you might have seen it change a little bit. So if we actually zoom in on some of these data points, you can see that the data doesn't exactly all lie on the line. Okay, it's off a little bit. Let's put some more noise in there. So you can see now the data is even noisier, but the fit, I mean the data roughly follows that of a line, but as you can see, it's not perfect. So basically the green line is the least squares curve fit, or linear curve fit, for this data. Okay, so we have that, and so you can see it roughly follows the line, but it's off because of the noise. So if we actually look at the values, so notice that this is the slope and that's the intercept. So if you recall the original function 3x plus 2, we can see it's actually pretty close. I'm actually getting very close to the actual slope and intercept. So even though we have noise, something gets. So notice here, when we had lower noise, we had a better estimate of the slope and intercept. Okay, and so notice we're getting, our estimates are not quite as good the more noise that we have. So noise can definitely affect that. So basically we use the command pin, pseudo-inverse. Okay, I'm going to show that you can also do it this way. So that slash is a left divide. So instead of pseudo inverse times y, I'm doing a left divide times y. And you can see we get the same kind of result. Okay. Now, because each time we go through, a different set of random noise is generated, then we'll get different values each time. So that is the left divide or the pseudo inverse. Next, we have SIMULINK. We want to talk about setting up, running a simple diagram, saving data in a scope, running a diagram from a script. So these are the basic SIMULINK commands we're going to talk about. SIMULINK is an add-on to MATLAB that is used for simulating systems. So it's very helpful in terms of being able to design a controller for a system and see what the response of that controller is when you apply it to the system. Okay, here we have the SIMULINK library browser, and we can go ahead and create a new block diagram here. So here's the block diagram, and now we can start adding blocks to this diagram to do simulations. Okay, so what's helpful is that you can actually have a simulation block tied to a set data in the workspace. So for example, I can define a system with this transfer function. And so in our block diagram, if we go here to commonly used blocks, transfer function, I can drag that over. So in dragging that over then, there it is, I can do different things. For example, well, first of all, I can, if I double click on it, it brings up its dialog box. So I can put in num and den. So as long as that numerator, as long as those variable names are defined in the MATLAB workspace, then we're good. So I'm going to go ahead and save that. And so now it's defined. I can now bring other things into the block diagram. So there's a constant. I can use a summer. Now I'm going to make a copy. This is going to be my controller, and now I'm going to put a scope over here. Okay, so this is, now I don't know if this controller is going to work or not, but well, so let's try something like, let's see. Oops. I need to do it in a regular polynomial form. I'm making this up. I'm hoping it's going to work. Let's see if it does. Okay, so I have a simulation diagram. And I can go ahead and do a simulation. Now, whenever I do a simulation, first thing I always go do is to the model configuration parameters. Okay, because there are some important things in there that define what's going on in our system. So, over here, I actually put in the parameters for the controller. I could also have defined those in my MATLAB workspace. Okay, so here are the parameters. Stop. So this is 0 to stop time. Stop time, that's I'm going to simulate up to that time. Now here are a couple things I always change. I don't know why they always leave it as these values. Those values are not very good. -8. Okay. So I always change those to 10 to the -8, both of those to 10 to the -8. If you don't change those, you tend to get poor simulation quality. So 10 to the -8, you get good simulation quality. It takes a little bit longer, but sometimes you can hardly even notice the difference in time. So basically, I have a closed-loop control system. I'm applying a constant input, which is basically a step, and so this thing is going to go through, and it's going to do that. So let's so we're all set to go. I can run the simulation. So here's the plot. Here's the step response the response of the system to that step input. And so there's the response. Now I can see I have a huge overshoot, and it doesn't settle at the value that I want it to settle. So this is not a particularly good controller, but at least it's stable. At least it's stable. So this is a simulation that we can do, and so that's an example of a simulation. I'm going to go ahead and clear a lot of this stuff away and do a different simulation. I'm going to clear that for now. Okay, so when it comes to system identification, we want to be able to do experiments, and so over here I can go over to sources, and I'm going to choose a different source. I'm going to choose band limited white noise. Then I'm going to go over here and choose, let's see, math operators. I'm going to go to sine function. Right, and then I'm going to go to a mux. So I'm going to take this signal. So this is band limited white noise. It has a sample time associated with it. In this case, 0.1 seconds. I'm going to change that to t, and I'm going to set the sampling period here. T equals. So this is basically going to give a random sequence that changes every t seconds. And then I put it through this sine function, which basically converts it into a random binary sequence like we saw before. I'm now going to go here to discrete and go to a zero order hold, which acts like a analog to digital converter, so that these are both discrete time signals. They go into a mux, which combines two signals into a single signal that now goes into our scope. Okay, so I can run this, and so here's the result. So the yellow is the random binary sequence that's coming out of here. The purple is the output of the system associated with that. And here you can see that that signal is quite small. I can zoom in on Y, and I can see that it's not 0. It's fluctuating around 0. And I realized I didn't set this sampling time here. I'm going to change it to be T. Okay, let's resimulate. So it didn't change much. So it meanders. Right. So this is the kind of data I would want to use in a system identification experiment. So in order to save that data now, so I can use it, I'm going to go over here to the parameters, and I want to do some things. First of all, history, I'm always going to uncheck that. I don't like that setting. It's a standard setting, and I always uncheck it because I don't like that. Second, I want to save the data to workspace. So I'm going to call it just data. And it's set to be an array, so I'm going to leave it as an array because that's the way I like it. And okay. So what's going to happen now when I run the simulation is that data is now available over here in the workspace. So let's see, where is that? There, data. So notice it's a 201 by 3. Okay, so it has 3 columns. Okay, so notice there are only 2 inputs. So what's the third data? Well, so here we have this. I'm going to go ahead now. I can use the data, so I can say T is equal to data. The first column. Notice this top one is actually U, so that's U is equal to data, 2, and Y is equal to data, 3. So I can extract the data from that. I can extract the various signals from that data matrix, and now I can plot it. So I can now run this, and it brings up a plot that has the basically the same responses I was seeing earlier. So notice we have the Y is small, but it's not 0, it's meandering. Okay, and so I can separate the 2 signals here, whereas they're combined together in this plot. So I have that I can do. And we can do FFT, we can do system identification using this data, and so forth. So this is an overview of MATLAB and SIMULINK, and also I can actually run this simulation from MATLAB. So I can do sim. And I haven't named this, so I'm gonna give it a name. Sim1. SLX, I guess, stands for Simulink Extra or whatever. I don't know. Anyway, So sim1. So when I run that, it runs the Simulink, and it gives this plot. And I'm not sure what happened, what was different, but it really my system got going a little different than it did before. So the noise can, or the signal input can really have a big, profound impact on what happens with the system. So before we had a very tiny signal, now we have this signal that is huge, or not huge, but significantly bigger. So notice that in this band-limited white noise, we have a seed. That seed basically defines so it's supposedly noise, random, but it's not random. It's what's called pseudo-random, which means that it will always be the exact same noise every time based on what that seed is. Okay, so if I change the seed to, let's say, let me give it a name, seed, CD equals 1. I'm just going to give it a different number as a seed. Boom, I get a different response. If I use the same seed again, okay, I get the exact same response. If I change that value, then I get a different response. If I use that same value, this same value again, I get the same response. So the system responds the same to the same input, but by changing the seed, I can change the random sequence. So if I want a random sequence every time, then I have to change the seed every time. Okay, and so you can choose the seed, for example, to be a function of the time, for example. And so if you look at the thousandth place or the hundredth place on time, you're going to choose a random number out of that. So there are different ways of picking random seeds, but so anyway, here we have Simulink. We've seen another number of features of Simulink. Okay, now we're going to talk about doing symbolic math in MATLAB. Here are some of the things we're going to talk about. The basics of symbolic math, working with polynomials, working with matrices. So these are the kinds of things that we want to look at in working with symbolic math. Okay, let's look at these symbolic math features of MATLAB. So in order to define a symbolic variable, we use sims. Okay, so that creates a symbolic variable. So A, S, B. We'll start there for now. And suppose I have a transfer function that is a polynomial over polynomial. Let's say it's so P is equal to 3 times S plus A divided by S plus B, S plus S squared plus 3S plus 2. So suppose that's what we have. If we run this program, oh, didn't like something. Okay, let's try it again. Had trouble. Click on that. Oh, it didn't like 3S. I have to do 3 times S. Here we go. So 3 times A, 3 times S, blah, blah, blah. So notice I did a divide S plus B, divide S squared plus 3S plus 2. And notice that it put it all in the denominator. Okay, so that's one way of putting it all in the denominator. Otherwise, we can just, again, put parentheses and write it out exactly the way it is here. Now, MATLAB has one feature. We can use the command pretty. And so it actually makes it look like a fraction. So, sometimes that's helpful to be able to see what's going on. So pretty is a good way to do that. Now, I also, since I use this to help me write homework assignments and things like that, you can also do something like this, LaTeX P, and it gives you what the LaTeX code for that looks like. Okay, so I use that from time to time. So there's pretty. So let's suppose we have now, let's say Q is equal to S plus 17 divided by S plus A. Okay, and so now I want to see what P plus Q looks like. So the addition of these two functions, and so notice it just writes it out. It does it that way. So suppose we want to now put this all over a common denominator. We can do something like this. Let's say R is equal to factor P plus Q, and it will try to factor it. And so notice it's in the denominator we have the nice factors like we would expect. In the numerator, it's a mess. Okay, it's a mess. So one of the things about symbolic math that you will often find is that you can get some horrendously huge expressions, and it's very difficult to see what's going on. So it might be helpful to do a pretty R. It might. In this case, it's not too bad. Definitely much easier to see than what we had before, but sometimes even this will give us an expression that is so complicated it's hard to look at. Well, we did P plus Q. What happens about if we do P times Q? Now notice I have S plus A here in the numerator, S plus A in the denominator. We should get a cancellation occurring. Let's see what happens. So notice the S plus A terms are gone. So it knows that it can cancel those things. So it actually goes through and does the algebra the way you would expect. And so it does some simplifying things. So factor is one way to simplify. We can also do simplify. That's another way of simplifying this. So in this case, notice it basically gave us a very similar result. So notice here it factored it here. It didn't factor it here, but this is still simple. Okay, so simplify is one way. Sometimes simplify doesn't simplify very well. Sometimes you need help simplifying, and there are other things that can be used. I'm here just trying to give you some basics of working with the symbolic math toolbox. So so let's suppose we have this function Q, and I want to take the inverse Laplace transform of that. So I'm going to do this now. Or let's do the inverse Laplace transform of P. So I can do little p is I'm going to define the variable t now as the time variable. So P is equal to inverse Laplace of P, comma S. So that's the variable, comma T. So it's in the S domain. When I take the inverse Laplace transform, my new variable is going to be T. So let's see what this does. Boom. So notice it does the inverse Laplace transform. Sweet. Okay, so we can use that. So it has the inverse Laplace transform. Similarly, if we had, let's say, W, equals e to the x minus 7t times cosine of 3, oops, doesn't like 7t, 7 times t, 3 times t plus pi divided by 4. So w is equal to Laplace of w comma t comma s. Let me go ahead and semicolon those. So here it gave us w. And so I can actually do a factor, pretty factor w. Boom. Square root of 2 over 2, or 1 over root 2, s plus 4 divided by all that stuff. So this will do Laplace transforms. Sweet. Inverse Laplace transforms. Sweet. Well, MATLAB will also do z transforms and inverse z transforms. So here I'm going to do z and k. So let's say v is equal to a to the power k times cosine of pi times k divided by 3. So v then is equal to z trans v comma k comma z. So when we run that, let me comment this out. So we get the z transform. Okay, so again we can do pretty factor v. Boom. Sweet. Now, since mostly in this class we're going to be using the Q transform, then we want to have it in the form that we're going to be using. So here we want to substitute now for Q z inverse. So notice z is equal to, or Q is equal to the inverse of z, or z to the power minus 1. So Q is equal to, we can put in Q to the power minus 1. So let's go ahead and do pretty factor v. Oh, didn't define Q ahead of time. So here, one of the things about the symbolic math is you always have to be sure that you define your variables ahead of time. There we go. Boom. So we actually have the Q transform now of this sequence. So what happens if I add pi divided by 2? Okay, so it changes the function, but we still get a valid function. So I can do Q transforms. So notice that here I substituted in Q to the power minus 1. Suppose now we have a transfer function. H is equal to z plus 1 times divided by z squared plus minus z plus 1. And z minus 1. Suppose we have this function. Oh, I'm sorry. Let's do this in the Q domain. Let's do this in the Q domain. So let's suppose we have something like this. Q squared times 1 minus 2q times q divided by 1 minus q divided by 1 minus 2 times q plus q squared. So suppose we have some function in q and we want to take the inverse q transform. Well, the first thing, so this thing does z transform, it doesn't do q transform. So if we want to now use the z transform, I first have to convert from q transform into z transform. And so the way to do that is I'm going to do this called hz is equal to subs, which means substitute, in h for z q to the power minus 1. And I'm going to go ahead and factor that. Factor. So what happens when we run that? Boom. So there's q should be z to the power minus. So when we run that, we have a function in z, and so now we can take the inverse z transform. So h is equal to iz trans hz zk. And choose k. So this is actually what happens when we take the inverse z transform. We get this function, which is kind of funky. So h is equal to k minus n choose k. So that's like a binomial function. Kronecker delta. Okay, so there's a delta function in here. So we get some funky things happening. Okay, and that's because we have repeated roots, so it's complicated that way. Let's change the function a little bit. Let's do that. Okay, that's going to change it. Let's run it. So we can see we get a more complicated function that we're dealing with now, just by that simple change. And notice that here, when it did the inverse transform, it left some of the things in terms of I. Okay, so that's kind of interesting. So let's do simplify here. So it didn't seem to simplify very much. Let's try factor. See if that. So there are a number of different things that can be used to try to do this, and it still didn't do very much. So it's it's always interesting to see how it's going to do some of these things. But I mean, this result is correct. It's just not very particularly helpful. So you can see it's got some quirks here. So anyway, this is the symbolic math toolbox. And these are all the MATLAB and SIMULINK functions I'm going to describe in this video. Thanks for watching.